Hello again. This is Math 1428, Remote Delivery for April 17th, 2020, and we're covering section 5.6 in your book. I encourage you to perfect your understanding by using these buttons in the YouTube video. Endurance is one of the most difficult disciplines, but it is to the one who endures that the final victory comes. Buddha was a wise person, and if your circumstances at all permit you to do so, I encourage you to stay the course. Your goals need not be deferred. Today's lecture focuses on applications and models of exponential growth and exponential decay, and also includes models of exponential and logarithm functions. The first model we're going to talk about is population growth. So if I have a function p representing the population, p of t is equal to p0, where p0 is the initial population at time 0, and this is e to the kt, and k is positive, meaning the curve is going to look like this. So this is a model for many kinds of population growth, rapid population growth, whether it be population of people, bacteria, smartphones, or money. K is called the exponential growth rate. Here's an example. We have the nation of Ghana, and in 2014 it had this population, and the exponential growth rate was this in percentage per year. These are the things we're to find. So to find the growth function, we're just going to substitute in. At t equals 0, we will call it 2014, and that gives us the initial p0, which I put here. The growth rate was this per year, and I write that as a decimal in the exponent. So this is the equation that we should have to represent this, and that's the answer to part A. We can graph this equation using a graphing calculator, and here this scale is in millions, and you do have to make sure that your window is chosen correctly, but you should be able to get this graph. Here we're estimating the population in 2018. Now in 2018, that means t is 4. So we substitute 4 into the equation. Either use your calculator directly on this, or you could use the calc menu to find out what x equal 4 is, and you find out it is about 28.2. In the last one, we say at this growth rate, when will the population be 40? Well, when we look at the equation, the population is over here, so that's where we put the 40. So we're going to be looking at this equation. 40 is equal to 25.8 e to the 0.0219 t. And we can solve this a couple of different ways. We can solve this algebraically, or we can use our graphing calculator. Algebraically, we'll divide both sides by 25.8, and then the t is in the exponent, so we'll take natural logarithms of both sides. And when you take the natural logarithm of e to the something, you just get the something. And now we have a linear equation in t. We'll solve t is equal to, we'll divide both sides by the coefficient 0.0219, and we'll get t is approximately 20. And so that means that after about 20 years, or in 2034, the population of Ghana should be about 40 million. The other way that we can do it is we can graph both sides. Here is one side. We're going to graph that as y2 equal 40. The other side is this one. We're going to graph that as y1. We find the point of intersection, and the solution again is about 20. I encourage you to perfect your understanding by trying this problem. Another important application is compound interest, and interest compounded in this case continuously, because then we do have a formula that looks like this. So we have an initial amount, p0 is invested, and the interest rate is k, and this is compounded continuously, and so this again follows an exponential growth pattern. Here's an example. Suppose that you took 2,000 invested. That means 2,000 is p0. and it's compounded continuously. That means this equation holds, and it grows to this amount in 5 years. Well, that means that when t is 5, p of t is this. So we have to solve this. Again, we can solve this algebraically by dividing both sides by 2000 and taking the logarithms of both sides and solving. We also can solve this graphically by graphing this side and graphing this side and seeing where they intersect. I encourage you to try this exercise to perfect your understanding. Now, it's worth noting that we can find a general expression for relating the growth rate and the doubling time. Because if we wanted the investment to double, we would say, oh, P of t is going to be 2 times what we started out with, 2 times P0. So if we divide by the P0, we'll get 2. Taking the logarithms of both sides, we have ln of 2 is equal to ln of this. Ln of this expression is going to be kt. So t is equal to ln of 2 over k. And here is an expression for the growth rate and the doubling time are related by all 3 of these equations. And note, importantly, that it does not depend on P0. Here's example 3 dealing with population growth. So now we're talking about the Philippines. The population of the Philippines is doubling every 37.7 years. What's the exponential growth rate? Well, we can just use the equation that we have from the box, and it is the natural logarithm of 2 divided by t. We insert the 37.7 here, and we get that the growth rate is, I change this to a percentage, it is 1.84% per year. I encourage you to perfect your understanding by trying this exercise. There also are realistic models of limited growth. And these are many applications because growth can happen in an unlimited fashion. There's only so much food and so much resource. So in some populations, there are factors, in fact, probably in every population, that prevent it from exceeding certain limiting values. So here's a model. This is called a logistics function. Notice that the exponential is in the denominator, and we have a negative kt. And so here's an example. This deals with a lake stocked with fish. There's only so much food for the fish to eat, and so it is restricted. So we have this kind of expression. We put the limit of the fish population is 2,500, so that is what goes up here in the numerator. The denominator is found to be this growth rate. So you can graph the function, and you can find the function after certain periods by plugging in the value for t. And so if you graph the function, you get this. Notice it is an S-curve. It starts out slowly, it grows rapidly, and then it starts to hit the limit. You can also use the table function to get some of the values that you want. And we were asking after 20 months, and in fact we put those values into our table and we got the values that we want. I would encourage you to perfect your understanding by trying this exercise. Another model of limited growth is provided by this function. You see it starts out at some place and then it grows. This is sometimes called a learning curve, because you can start learning how to type, for example, and you improve very rapidly for a while, but eventually you reach the limit of your agility and physical capacity. We now turn our attention to exponential decay. Now this equation is just like what we talked about before, except instead of having e to the k, where k was greater than 0, is e to the minus k, where k is greater than 0. As we talked about in the growth section, or in earlier the graph section, this is going to be a decreasing curve like this. And so this is an effective model of decline or decay of a population. As an example of the decay of a radioactive substance, the initial amount is P0, and there is less and less over time. K is called the decay rate. Here, instead of doubling time, we talk about the half-life. And so the half-life of bismuth is 5 days. That means that half an amount of radioactive bismuth will cease to be radioactive in 5 days. We can find an expression, as we did before, for the doubling rate for the relating the decay rate and the half-life. So we say, at what time do we have 1/2 of what we started out with? And this is the equation that governs it, and we're going to solve this for t. So we divide both sides by p0, we get 1/2 here. This is going to be the natural logarithm of 1/2. Now the natural logarithm of 1/2 is the same thing as minus the natural logarithm of 2, but over here we get minus kt when we take the natural logarithm there. So t is equal to the natural logarithm of 2 divided by k. And this box formalizes what we found there. So there's a relationship between k and t, and any of these three equations can be done. And note that the relationship between decay rate and half-life is the same as the relationship between growth rate and doubling time. And as you think about that, that actually makes sense. One huge application of this is called carbon dating. And here are some Dead Sea Scrolls that were found. And so the half-life of carbon-14, which is used as a trace element here, is 5750 years. So the percentage of carbon-14 present can be used to determine the age of these things. This is a linen that the Dead Sea Scrolls were wrapped in, and it had lost 22.3% of its carbon-14 value by the time it was found. How old was the linen wrapping? Well, you can find K using the formula that we just have, and that gives us this function for the decay. So we can say that now if we've lost 22.3%, we still have 77.7%. So 0.777 P0 equals P0 times this. So we divide both sides by P0, it cancels out. We take logarithms of both sides. We divide by the coefficient of t, and we get that these Dead Sea Scrolls were over 2,000 years old. You can perfect your understanding by trying this suggested exercise. We also talk about fitting curves because this is of interest, this is of interest, and this is of interest, and even this is of interest. So in fitting these curves, we can use our calculator function. And so in addition to polynomial models, we can now do logarithmic and exponential models, and your regression functions have these. So here health costs have increased exponentially over the past few decades. Here's some data. So we use graphing calculator. We plug this data in to our tables, and we get a model that looks like this. The model that we're looking at is y equals a times b to the x. That's the exponential model. We fit the data to this curve from the statistics menu, and we find these values. Notice that r is very close to 1, meaning that it fits the data very well. So you see we ended up with this being our equation, and the correlation coefficient is close to 1. That means it's a good fit. If we did a scatter plot, as we're asked to in part B, we get this. And we can also get the value in any years by substituting that value into our calculator. I encourage you to perfect your understanding by trying this problem. And I note on some graphing calculators there may be a regression feature which has the exponential base. If not, you might want to find such a function by using this conversion. You see, whenever I have e raised to the ln b, that's just going to be b, so this is b to the x. So I can convert from base b to base e using this conversion factor. So for the equation that we had previously, and applying that, what we're going to do is I'm going to put the value that I had for the natural logarithm of b up here, and that gives me a model based on e. So now, more than ever, Time is precious. Each day must count. Do the math. It will make you strong. And now more than ever, take care of yourself and of each other. See you in class.